Okay, I'll let it derive the electrostatic force using the Euler-Lagrangian equation. I will start by reading this problem below. Let the position Q be represented by R to measure any change that defines the distance. There are the electric field lines from a positive charge interacting with a particle that has an opposite charge from it. What would the concluding force be to represent the interaction between these two charges? Regard the radial spread of the electric field lines of the two charges in 3 dimensions. Okay, as these two charges are attracting each other, they're following a certain velocity, and I will define this velocity using the length element of the sphere. And the reason why I'm doing this is that I'm regarding the 3 dimensions, and I'm not respecting any rotation. So I will define the velocity over here for v equal to L dot. And L dot is Newton's notation to represent the time derivative of L. Now I can write the length element of the sphere vector while distributing the time derivative across it. Now I can use Newton's notation Now, if you're wondering why theta and phi are being derived regarding these two vector components, is that the radius at this direction, or these two directions, will be treated as a constant. However, the radius following the radius direction will be treated as a variable, as a non-constant variable. I will put it that way, not confuse anyone. Now, since I define the velocity vector here, I can define the kinetic energy. And the kinetic energy, we all know, is half times mv squared. And I can replace the v with L dot. Now, before going any further, I am squaring a vector. And to square a vector, you have to take the dot product of itself. And Newton's notation helps a lot to not write this long vector. And I'll just copy and paste it within the parentheses. Now, since I'm taking the dot product of this vector of itself, it should render this solution. r dot squared plus r squared theta dot squared plus r squared sine of theta squared phi dot squared. And I'm forgetting half times m. Now I can define the Lagrangian since I already derived the kinetic energy. Lagrangian, as mentioned before, is the difference between the kinetic energy and the potential energy. Now we already have the potential energy defined right here. So I can first write the kinetic energy or just copy it. And I can subtract on the potential energy. And notice there are two negatives. So I'll turn this Lagrangian into a sum. Now I'm going to reintroduce the Euler-Lagrangian equation, but this time I'm going to use the variable r instead of q. Now we're going to start with the left side of the equation. And more specifically, I'm going to start with this partial derivative. Now note, since I'm deriving respect to r dot, the rest right here are just going out to 0. So the result will be half times m 2 times r dot, which will be 2 over 2 m times r dot equaling to m times r dot. Now I'm going to reintroduce the left side of the Euler-Lagrangian equation. Now we already defined this right here and a result to be m times r dot. I'm going to differentiate with respect to time, m times r dot, where mass is constant, so I can take it out. And now I'm going to differentiate just R dot. I mentioned in the other video, since R dot is a position, and R dot will equal to the time derivative of R, taking the time derivative of R dot should give me double R dot. And that will equal to an acceleration. So I can write it right here. So it'll be mass times double or R double dot, and that will equal to mass times acceleration, which that will equal to a force. And let's do the right-hand side. And I'll do it below. Now I'm going to copy this Lagrangian right here. This part is going to be a little tricky because while R dot right here will cancel, we do have R variables right here. So the derivative, the partial derivative will be half times m 0 plus 2r theta dot squared plus 2r sine of theta squared phi dot squared. Now we're going to derive this right here. We're taking the partial derivative of 1 over r, which will be taking the partial derivative of r to the first power, and that will equal to negative r to the negative second power, and that will equal to minus 1 over r squared. So we'll have a minus sign here, write the electric constant right here, make it a little prettier. I'll write the product of these two charges, and it'll be over r squared. Now I can go further. Where I'll distribute the m on the left side. I can cancel out the 2's. This will be m times r times theta dot squared plus m times r times sine of theta squared times phi dot squared minus the electric constant, and then the products of the charges over r squared. Now this defines the electrostatic force here. We have our answer. And since the charges are attracting, we'll have a negative sign, and we can define the Coulomb's law force. I'll put it in a square. However, you notice this value right here that represents the centrifugal force. Since I'm using spherical coordinates and we had 3 dimensions of freedom, idea is, I would think it would be best represented in 2 dimensions instead of 3. It'd be kind of complicated. But we have a rotation. And the idea is, even though we have the origin right here, let's say there's a ball right here, and it's spinning, it's going this direction. And let's say, for instance, right, when the moment the ball reaches to this vertical level, it snaps. And it's going to follow a tangent. And this tangential direction will have it follow a straight line. However, the ball didn't snap, so it's going to continue on a rotation. So now you're going to have an inertial pressure that feel like the ball is being smushed, or let's say, for instance, like some object that's following the ball and it's feel like it's being smushed by the rotation. And that's basically the centrifugal force being this inertial pressure. However, the main focus of this video is to conclude this value, where we had the electrostatic force. And that's it. Thank you for whoever's watching.